Okay, polyphase power is an area that we're going to get into later, but this is just an introduction. What we're talking about with phase shifts, the important application of phase shifted sine waves in electrical power systems in the utilities area. In this case, we're showing a three-phase sine waves of power um, being sourced. You can see phase 1, phase 2, and phase 3. In each case, they're 120 degrees separated from each other. And typically, in a system where you have three-phase power, like your residential neighborhood, you normally don't get all three phases. The phases are separated out and managed and distributed into a neighborhood so that the power is distributed properly between the residential houses. So anyway, this is just giving you a depiction of what the three-phase system looks like in terms of shifted phase shifted sine waves. So we'll get more we'll get back into that and more later on. I think you had a introduction to that in your DC course right at the end. So we'll see that later. So now we need to look at how do we develop the mathematical relationships to allow us to work with these phases and these AC signals. So a sine wave can be graphically represented by voltage or current values on the vertical axis and by angular measurements, degrees or radians, along the horizontal axis. So the graph can be expressed mathematically as we're going to find out here. So we need to look at the mathematical analysis of a sinusoidal wave so that we can state the sine wave formula clearly so we know what we're looking at mathematically to match what we're looking at. And then we're going to find the simultaneous values using the sine wave formula. So in looking at this, again, we go to a simple generalized graph of a sine wave, one alternation, so that we can fundamentally look at what's going on here if we were to take a snapshot in time or stop the sine wave in one alternation. Typically on an oscilloscope you will be able to see that it'll appear to be stopped, although it's occurring over and over again. So the generalized graph of one cycle of a sine wave can be seen here. The sine wave amplitude is the maximum value, in this case, of voltage or current on the vertical axis. So whenever we refer to the amplitude of the sine wave, typically we will be looking at on the oscope the voltage, maximum voltage of the sine wave. Angular values then run along the horizontal axis. The variable y is an instantaneous value that represents either voltage or current at a given angle. In this case, we use the angle theta. If you're not familiar with that sign, typically we use theta and we use phi, and we'll see that later when we're trying to distinguish between two different angles. The symbol then theta is the Greek letter. All electrical sine waves follow this specific mathematical formula. So if we look at this by parts, you can see that the mathematical expression says y, which is the value on the y-axis, is equal to a, the amplitude, times the sine of the angle of interest, angle theta. So this formula states that at any point on the sine wave represented by an instantaneous value y is equal to the maximum value of the amplitude a times the sine of the angle at that point. So we have to know at least three of those values. Okay, we have to know the amplitude, we have to know the angle theta, and that will determine the value y. Okay, so this will become important as we get deeper into vectors that we call phasors. For example, a certain voltage sine wave has a peak value of 10 volts. You can calculate the instantaneous voltage at a point 60 degrees along the horizontal axis as follows, where y equals lowercase v, the AC voltage, and the amplitude is equal to V sub P, the peak voltage. So now if we take those values, plug them into the sine wave formula, we have little v, the AC voltage, instantaneous, is equal to the peak voltage, V sub P, times the sine of theta. So 10 volts times the sine of 60 degrees gives us 10 volts times 0.866, or 8.66 volts. As you work with sine and cosine values more, you'll start to where you won't need your calculator to calculate the sine of angles that occur over and over again. Sine of 30, sine of 0, sine of 60, sine of 90, sine of 180. You'll start to get used to them. And again, what I recommend you do is every time you come up with a new value, so you don't have to deal with punching into the calculator every time, is just write it down in your notebook and keep track of it. It'll give you a shortcut. The thing to keep in mind, though, is that 0.866 is actually a bigger number. So if you want accuracy, you always take the sine of, in this case, 60 degrees. So the figure 1125 on the right shows a particular instantaneous value then of the curve, and you can find the sine of any angle on almost any calculator by first entering the value of the angle, 60 in this case, pressing the sine key, and verify that your calculator is in degree mode. So if you're using the Casio calculator, you can see right here, there's that button right there is the sine, right next to the cosine and the tangent. So get used to using those values. Okay, so the sine wave formula. Expressions for phase shifted sine waves. Next, then, we're going to look at those phase shifted values and use what we've learned with the sine formula to calculate things that have been shifted. So we'll stop there and come back to using the sine wave formula for shifted values.